Today we're going to study nth roots and rational exponents. The objectives of this lesson is to simplify radicals and to simplify expressions in exponential or radical form. A perfect square is the square of a whole number 0, 1, 4, 9, 16, 25, and 36 are, for example, the first 6 perfect squares. And a perfect cube is the cube of a whole number 1, 8, 27, 64, 125, and 216 are the first 6 perfect cubes. This idea can be expanded to perfect powers of a variable for any radicand. The radicand x to the n is a perfect power when n is a multiple of the index of the radicand. A quick way to determine if a radicand x to the n power is a perfect power for an index is to determine if the exponent n is divisible by the index of the radical. And here we have an example. The fifth root of x to the 20 power. This, if you notice, 20 is divisible by the index 5, and x to the 20 is a perfect fifth power. And here we have a really useful property for the simplification of roots or radicals, and it is the product property of nth roots. And this property says the following: the nth root of a times b is equals to the nth root of a times the nth root of b. So let's see some examples. If we need to find the cubic roots of 32, the cubic root of 32 is not exact, but we can simplify this radical. And for a moment, I can see that 32, actually we can find the prime factorization, but sometimes we can do this mentally. If the 32 is the same as 8 times 4, so this becomes equals. The cubic root of 32, it will be equals cubic root of 8 times the cubic root of 4. The cubic root of 8 is a perfect cube, so the cubic root of 8 is 2, because 2 to the third power is 8, and the answer will be 2 times the cubic root of 4. The cubic root of 4 is impossible to get a whole value, an exact value, so it would be a decimal if we need to get rid of the radical, but we don't want decimals, so the answer would be 2 cubic root of 4. Let's see another example. The cubic root of negative 250. Negative 250 can be expressed like negative 125 times 2, and the cubic root of 125 will be exact because negative 125 is a perfect cube. So this becomes equals using the product property. The cubic root of negative 125 times the cubic root of 2. And this will be equals the cubic root of negative 125 is negative 5, and the answer is negative 5, final answer, negative 5 cubic root of 2. And one more example, the fourth root of 48. Maybe this case is difficult to think of breaking down the 48 as a product of two numbers, so one of them is a perfect fourth power expression. So in here what we can do, and let me make clear that we could have done that in the previous ones, is to find the prime factorization of 48 to see if I can get a number or an expression that is raised to the fourth power, so we can take the fourth power of that expression and we can get rid of the radical, at least with one of the expressions that we're going to break this number into. So 48, the prime factorization, 48 is divisible by 2, and 48 divided by 2 is 24. 24 again is divisible by 2 is, and 24 divided by 2 is 12, and 12 can be divided again by 2, and the answer will be 6. See that so far we have 3 times the value 2. 12 divided by 2 is 6, and again we can divide by 2, and we will get 6 divided by 2, that is 3, and 3 divided by 2, we cannot continue dividing by 2, but 3 is divisible by 3, so the answer at the end, we have all the factors in here. So 48 is the same as, if we express it like a product of as a product of prime factors, 48 is equals to the 4th power, because we count the number of times that appears the 4 is the 2 is 4, so it will be 2 to the 4th power times 3. So we can use this principle in the fourth root of 48, and this will be equals the fourth root of 2 to the 4th power times 3. Why 2 to the 4th power? Because when we divide or we find the prime factorization, the 2 appears 4 times. So it's 2 to the 4 power times 3. And this will be equals, using the product property of nth roots, the fourth root of 2 to the 4 times the fourth of 3. And the fourth root of 2 to the 4th is, we can actually, the answer is 2, so we can divide the power 4 with the index 4, and the index and the radical and the index will be gone, and the answer will be only 2. So the answer is 2 fourth root of 3. And here we have some principles or some ideas, some rules that we can use to simplify radicals using the product rule. Number 1, if the radicand contains a coefficient other than 1, we can write it as a product of two numbers, one of which is the largest perfect power for the index. Second, we can write each variable factor as a product of two factors, one of which is the largest perfect power of the variable for the index. 3, we can use the product rule to write the radical expression as a product of radicals. Place all the perfect powers under the same radical. And 4, we can simplify the radical containing the perfect powers. So we're going to make some examples to make this clear. So let's make some examples where we can simplify radicals, and let's begin finding the square root of 72. If you don't know how to break 72 into two numbers, such one of them is a perfect square, what you can do is to start trying prime factorization. 72, I know that is divisible by 2, and the answer is 36. At this point, if you want to continue finding the prime factorization of this number, you can continue, but I noticed that 36 is a perfect square. I know that the square root of 36 will be exact, and it will be 6. So we can stop at this point, and 72 will be equals square root of 36 times 2. Then I have the square root of a product, and I can use the property of nth roots for the product, and this will be equals the square root of 36 times square root of 2. The square root of 36 is exact, it is 6. Square root of 2 is not, so we leave it like that, and the answer for this exercise is 6 square root of 2. We have another exercise. In this case, we're going to use variables. We need to find the fourth root of b to the 23rd power. 23 is not divisible. The power of 23 is not divisible by 4. So the answer will be not exact. I need to have a radical in my final answer. But I can do the following to simplify this. And it is the following. 23 divided by 4, I know that it's not exact, but there it must be a value close to 23 that is divisible by 4. So I need to find the closest value to 23 that I know that is divisible by 4. If you think a little bit, that number, it is 20. So 20 will be divisible by 4, and the answer will be 5. So what I can do in here is to express b to the 23rd power as the product of two numbers. One of them will be 20, and the other one b to the 20, and the other one b to the third power. So this is equals the fourth root of b to the 20 times b to the third power. Remember that there is a product property for exponents that when they have the same base, we copy the base and we add the exponent. So b to the 20 times b to the third power is the same as what we have at the beginning, b to the 23rd power. Now at this point, and now that I have a product inside of the radical, I can break down by using property this as the following. Fourth root of b to the 20 times the fourth root of b to the third power. And what will be the fourth root of b to the 20? Do the following. I know that 20 is divisible by 4. So 20 divided by 4 it will be 5. Well, I don't need the radical anymore. It will be b to the fifth power times the fourth root of b to the third power. And I want you to notice the following. When the radical is simplified, the radicand doesn't have a variable with an exponent greater than or equal to the index. So in the previous answer that we just found, notice that the fourth root of b to the third power follows this. The radicand, the power in the radicand is 3, b to the third power, so that's a radicand and the power is 3, and this value is less than the index that is 4. So I know that the expression with radicals is simplified when this happens. And here we have more examples. Let's find the cubic root of 16x cubed y to the 6th power. The cubic root of this expression, let's begin with a number, the cubic root of 16, maybe we don't figure it out. So let's find the prime factorization of 16. 16 is divisible by 2, and the answer is 8. At this point, we can continue finding the prime factorization of 16, but I can make a stop because I know that the cubic root of 8 is 2. So 16 will be equals to 8 times 2. So let me replace this into my expression. It will be equals cubic root of 16 instead of 16, 8 times 2 times x cubed times y to the 6th power. Then I notice that I have some of these factors inside of the radical symbol that are perfect cubes. 8, x cubed, and y to the 6 are perfect cubes, so I put them together as a cubic root of that times the cubic root of 2 that I know that is not a perfect cube. And then I take the cubic root of 8, that is 2, the cubic root of x to the 3rd power, that is x to the 1. How do I know that is x to the 1? Simple, copy the base, x, and divide 3 by 3. The power with the index, it will be x to the 1. And y to the 6, do the same, copy the y, and divide 6 by 3, power by the index, and it will be y squared. And the answer at the end is 2xy squared times the cubic root of 2. Let's make another example. Let's find the negative 4th root of 32, x to the 18 times y to the 31st power. And let me take care of the number. Try to find out the 4th root of 32 is not that simple. So what I do is to find the prime factorization of 32. And I divide by 2, and dividing 32 by 2 is 16. 16 again is divisible by 2. This is 8. I can continue divided by 2. 8 divided by 2 is 4. 4 is divisible by 2. And 4 divided by 2 is 2. And 2 can be divided by 2, and it is 1. So, out of this prime factorization, the prime factorization of 32 is 2 to the 5th power. But since I'm finding the 4th root, it's a good idea to express 2 to the 5th power like 2 to the 4 times 2. And taking care of that also, taking care of the variable expressions, I notice that x to the 18 is not divisible by 4, but I can find out a number that is close to 18 that is divisible by 4, and that number is 16. And so x to the 18, it will be equals to x 16 times x squared. And the same can be done with y to the 31st power. I look for a number that is close to 31 that is divisible by 4, and that number that is closer, the closest one to 31 that can be divided by 4, that is divisible by 4, is 28. So y to the 31 expressed as y to the 28 power times y to the 3rd power. So this expression, guys, becomes equals. Notice that in here, the idea is to put together all those under a radical symbol that are divisible by 4 times the 4th root of all those that are not divisible by 4. So this becomes equals the negative 4th root of 2 to the 4th power x to the 16 times y to the 28 times the 4th root of 2x squared y cubed. And this will be equals negative. What it would be the 4th root of 2 to the 4th power? Easy, divide the powers. 4, the power 4 by it will be 1, so it will be 2 to the 1. X to the 16. What will be the 4th root of x to the 16? 16 divided by 4 is 4, so it will be x to the 4th power. And what will be the 4th root of y to the 28? 28 divided by 4 is 7, so y to the 7th power. Times the 4th root of those expressions that we can simplify. 4th root of 2x squared y cubed. Notice that in all these factors inside of the 4th root, all of them are less than the index 4. So the final answer is negative 2x to the 4th power y to the 7 times the 4th root of 2x squared y cubed. And again, when the radical is simplified, don't forget this, the radicand doesn't have a variable with an exponent greater than or equal to the index. Let's see another useful property of nth roots, and it is the quotient property for nth roots. And this property states the following: the nth root of a over b is equals the nth root of a over the nth root of b. And there is a condition: b cannot be 0, because we cannot divide by 0. It will be not possible. Divided by 0 is not possible. So let's make some examples, easy examples. Let's find the square root of 81 divided by 100. By using the property, what it can do is to get the square root of 81 over the square root of 100. And in this case, the square root of 81 is exact, the same as the square root of 100. Square root of 81 is 9, and the square root of 100 is 10. So the answer is 9 over 10. And 9 over 10 is a fraction that cannot be simplified. So we leave it like that. We have one more example. And in here we have the square root of 75 divided by 3. And I noticed something. If it is possible to simplify the radical, the expression that is under the radical symbol, let's do it. 75. We could have used the property square root of 75 divided by the square root of 3. But if I notice that something before the property can be done, let's apply the property. And this becomes equals the square root of 25 over 1, or just the square root of 25. And we know that the square root of 25 is equals 5. And we didn't need to use the property of the quotient for radicals because we simplify first. Let's make more examples where we can apply the quotient rule for radicals. And here we have the cubic root of 64x to the 6th power over y to the 12th. So by using the property, it will be the cubic root of 64x to the 6th over the cubic root of y to the 12th. In this case, I notice that these expressions can be simplified are exact. The cubic root of 64 is a perfect cube. If you don't see it, you can find the prime factorization. And the cubic root of 64, it is 4. 4 times 4 times 4, it will give us 4. X to the 6th power is a perfect cube because 6 is divisible by 3. And the expression at the bottom, cubic root of y to the 12th, that expression also is a perfect cube because 12 is divisible by 3. So the answer to this, it will be equals 4x squared y to the 4th power. Let's make another example. And in this case, let's find the square root of 64x to the 5th power over the square root of 2x to the 3rd power. And in this case, guys, I noticed that 64 is divisible by 2, and that x to the 5th power can be simplified with x cubed. So what we can do is to reverse the property of the square roots, and we have in here like the right side of the property, and we can go to the left side, and we can get only one radical. So this becomes the square root of 64x to the 5th power over 2x to the 3rd power. Then 64 is divisible by 2, and it would be 32, and x to the 5th power over x to the cubed power, we can copy the base and subtract the exponents. So this becomes the square root of 32 x to the 2nd power. And then this is equals, breaking, I know that 32 can be expressed like 16 times 2. If you don't see it, you can find the prime factorization. And 16, I know that is a perfect square. Square root of 16 is 4. So this would be equals this expression. Square root of 16x squared, those all together, 16 and x squared are perfect squares, times the expression that is not a perfect square, square root of 2. And this becomes 4x square root of 2. And here, guys, we need to assume, we need to have that clear because we're taking square roots, that the value of the x represents a positive number. So the answer is equals 4x square root of 2. And let's make another example. Let's find the fourth root of 3a to the 6th power b to the 5th power over 16a to the negative 2 and b to the 13th power. Again, I notice that I can, inside of the radical symbol in the radicand, I can make some changes or some simplification. 3 and 16 is nothing to do with it, but a to the 6 and a to the negative 2 power are the one at the top, one at the bottom, and we can use the quotient property to simplify that. And when I use the quotient property, a to the 6 divided by a to the negative 2, we apply the quotient, and what we do with the powers is subtract. So it will be a to the 6 minus a to the negative 2. But a to the 6 times minus negative 2 will be positive 2, so we'll be adding, and that becomes a to the 8. And b5 will be cubed, same idea, but I apply the following. Which one has the greatest power, b5 or b cubed? B to the 13th power. And I notice that b to the 13th power that is at the bottom, it has the greatest power, so I leave the b at the bottom and I subtract 13 and 5. So this becomes equals fourth root of 3 over 16 is nothing that I can do with that, times at the top 3a 8. Remember that we add a and 2 because it was 6 minus negative 2 over 16b to the 8. 8 because 13 minus 5 is 8. Now, this will be equals. I notice that I can take the root of a to the 8. So I take it like that. So I use the product property at the top. So I express the top as the fourth root of a to the 8, because that expression is a perfect 4-power expression, times the fourth root of 3, that is not a perfect fourth power expression, or the fourth root of 16 and b to the 8. If you find the prime factorization of 16, you're going to notice that the prime factorization of 16 is 2 to the 4th, so that is a perfect fourth power. So this becomes equals. What it would be the fourth root of a to the 8? It will be a to the second power. 8 divided by 4 is 2. Times the fourth root, we cannot simplify it. Times or over. The fourth root of 16, it is 2, because 2 to the 4th power is 16. And times b to the second power. Why b to the second power? Because the power 8 is divisible by the index 2, so it will be b to the second power. So the final answer, it is squared times the fourth root of 3 over 2b squared. And how do I know that a radical expression is in simplest form? So here we have some guidelines that can help us to determine if a radical expression is in simplest form. Number 1, no perfect powers are factors of the radicand, and all exponents in the radicand are less than the index. Second one, no radicand contains a fraction. And number 3, no denominator contains a radical. So every time that you simplify a radical, you can check these things or these rules or these guidelines to check the radical expression is in simplest form. Now guys, let's see what is the connection between radicals and rational exponents. So we're going to study in this part of the section rational exponents. In this part of the lesson, we're going to learn how to express a radical expression as an exponential expression, as an expression in exponential form. A radical expression can be written using exponents by using the following procedure. And before we see the expression that is going to let us to write any radical in exponential notation or in exponential form, let's make clear the following. When a is non-negative, the a is the radicand expression under the radical symbol, the n can be any index. But when the a, the radicand, is negative, the index must be odd. Why this condition? Because if the a is negative, you cannot take the square root, for example, of a negative number. So it would be not real. And we need to guarantee that the expressions that we're working with in this section, this lesson, would be real numbers. So the n, if the a is negative, the n must be odd. And let's see the expression that we need to know. The nth root of a is the same as a to the 1 over n. So this is the expression that allows us when we have a radical, the nth root of an expression a, for example, and I don't want that expression in radical form, it would be equals to a to the, notice that the power is a fraction, and the numerator is 1 over the n, that is the index. So nth root of a equals a to the 1 over the index. Let's see an example of this, or some examples. What would be the square root of 7 as this expression with a radical in exponential form? It would be 7 raised to the 1 over the index. And what is the index? I don't see any number in the index. But when that happens, I know that the index is 2. So the 7th root, the square root of 7, it would be equal 7 to the 1/2. Let's make another example. What would be the cubic root of x in exponential form, or an expression without radicals? It will be x to the 1, because x is x to the 1, so x to the 1 over the index. And what is the index of this radical? 3. So the cubic root of x, it will be x to the 1 over 3. And we have one more example, and it's the 9th root of 3x plus 7z to the 4th power. Notice that in this one we have a sum inside of the radical symbol, so the radicand, it is 3x plus 7z to the 4th power. So how can I use the property that we are learning in this exercise. What we're going to assume here, guys, is that inside of the radical, we have an expression, we have parentheses, and it says something like this, parentheses, 3x plus 7z to the 4th power, everything raised to the, since we don't want to change this, to the power 1. So this becomes equals, in parentheses, 3x plus 7 to the times z to the 4th power raised to the 1 over, like we did before, 1 over, and the index that is 9. Now, what if we have an exponential expression and we don't want to see this expression in exponential form and we want to see it in radical form? Or maybe we need to simplify this expression that is in exponential form, but we cannot see how to simplify it. What we can do is to reverse the process. So if I have an expression in exponential form, we can write it in radical form. So let's see. If I have a to the 1 over n, this expression is in exponential form, what I can do is to reverse the process, taking care of the n, especially the n that is the denominator of the power, and the n becomes the index when we write this like a radical. So this is equals to, or equals, the nth root of a to the 1, or just the nth root of a. So this is reversing the process that we used in the previous slide, in the previous examples. So now, let's make some examples. What if I have 15 to the 1/2? And this is not in radical form, and I'm interested on see what it would be 15 to the 1/2 in radical form. Take care of the 2, the denominator of this power, and it's 2, so this will be equals to the square root of 15 to the 1, or just square root of 15. Let's do one more. What if I have b to the 1/3? The index, it will be the denominator of the exponent, or the power of b to the 1/3. It is 3, so this will be the cubic root. B to the 1/3 equals cubic root of b to the 1, or just cubic root of b. Now let's see how can be any radical expression be written in exponential form, or any expression in exponential form in radical form. So what I mean is, what happens if I have an expression like the nth root of a to the m, and I need this in exponential form? So let's see. For any non-negative number, a, and integers m and n, the expression, the nth root of a to the m, it will be equals, notice that in the next, this will be equals to an expression in radical, but look at the position of the m. It will be equals to the nth root of a raised to the n power. So the m can be taken out of the radical, and it would be equivalent. It will be exactly the same value. And then this will be equals, I don't want radicals, I don't want the first radical or the second one, I need an exponential notation. So this will be equals to a raised to the m power divided by the index. So a to the m over n. The power m, the m represents the power m, and the n represents the index. So let's make an example to illustrate this. What if I have the expression b to the 2/3, and this is obviously in exponential form, and I need a radical expression? So I look at the power, that is 2 over 3. I take care especially the denominator, that is 3, and this becomes the index. So this expression equals the cubic root of b to the 2nd power. And what if I need that radical expression, but I don't want these 2 to be inside of the radical, as a part of the radicand? I can take it out, and this will be equals the cubic root of b, and everything raised to the 2nd power. Let's make another example. And look at the expression 8x squared minus 9y raised to the 7 over 3. Again, this is an exponential expression, and I'm interested in writing this in radical form. Look at the power, 7 over 3. The index of that expression, the denominator, sorry, that expression is 3. The 3 becomes the index, so this becomes equals the cubic root of 8x squared minus 9y raised to the 7th power. And I can take one more step just in case you don't want the 7 inside of the radical. And this is equal to the cubic root of 8x squared minus 9y, x squared, the cubic root of 8x squared minus 9y, and this raised to the 7th power. Now we can use this, what we have learned about rational exponents, radicals, and exponential form to evaluate expressions. And in here we have the following. If I have the expression 125 raised to the 2/3 power, and you don't see a way to simplify it in the way that is given, you can try it out to express it in radical form. So this will be equals, again I'm taking care of the exponent, and I notice that the exponent is 2 over 3, and especially the 3 that is the index. So this will be the expression 125 raised to the 2/3 power equals to the cubic root of 125 to the second power. If still I get confused with the 2 power that is inside of the radical, I can take it outside by using the definition that we saw previously, and this is equals to the cubic root of 125 and everything raised to the second power. Now I know that the cubic root of 125, it is exact, and the cubic root of 125, it is 5, so this becomes 5 to the second power, and 5 to the second power is equals 25. Let's see another example. I have the expression 81 raised to the negative 3 over 4 power. First of all, let's take care of the fact that it's negative, and by using one of the properties of exponents, I can get rid of the negative by writing this expression like 1 over 81 raised to the 3/4 power. Now in the next step, let us take care of the exponential notation that we have, and maybe we change this exponential form to a radical form. We can simplify this, and this becomes 81 to the 3/4. 4 is the index, so this will be 1 over the 4th root of 81, and out of the radical is one of the properties that we saw before, it will be raised to the 3rd power. So we can get the 3 out of the radical, so it will be the 4th root of 81 and raised to the 3rd power. In the next step, it will be 1 over. What is the 4th root of 81? You can find the prime factorization of 81, and 81 is the same as 3 to the 4th power. So the 4th root of 81, it would be getting rid of the exponents, 3 to the 4, 4 divided by the index, it will be only the 3 the base. So the 4th root of 81, it will be 3. And this becomes 1 over 3 to the 3rd power. And 3 to the 3rd power, it is equals 27. So my final answer is 1 over 27. Okay, we just finished the lesson of this week, and I hope that everything is clear, and in case you have any questions, we can answer those questions in the Zoom meeting that we're going to have this week.